Hello and welcome, everyone. And thank you all for joining us here today for the FDL Europe AI State of the Art Showcase 2024. We have a lot of exciting and interesting things to share with you today. We'd like to start by setting the scene. FDL Europe is a unique thing. Our teams do applied AI research at the highest level on problems that are fiendishly difficult. These are high risk, high reward problems. That is, they're problems, which our computer science folks would call non trivial. So today, you're going to get a really deep understanding of some really interesting problems, the relationship of clouds to global warming, and ESA's CloudSat mission, new ways of measuring biomass, which of course is the best way to store the carbon that is doing the heating, understanding state of the art in foundation models, the technology behind the current AI boom, flooding, which is an outcome of global heating. And finally, you'll get a new way of understanding our vulnerabilities living inside a star, which threaten our technological civilization in ways that we are still just waking up to. So the bottom line is you're going to learn a lot. And you're also going to get a front row seat as you learn about high RL or technology readiness level applied AI. Now, before we get started with our researchers, I'd like to introduce the director of FDL, the director of the CEO of Trillium Technologies. If you'll join me on the stage, please, James Parr. James, take a couple of minutes. Good to see you, James.
Hey, everybody.
Take take a couple of minutes, if you would, to talk to us about FDL and the journey we've been on for 10 years and really focusing on why this work is meaningful. Why should anyone be paying attention to what we've been doing with these researchers, many different researchers for the last 10 years?
Thanks, Jonathan. Yes, we're very lucky, and I say that because our colleagues at ESA and the Luxembourg Space Agency have had the sort of vision, or at least the kind of the faith in us to really tackle some really difficult problems. And we say that FDL and FDL Europe is about high risk, high reward AI. These problems are really difficult. They're open problems. As you said, they're non-trivial, which is how our comp sci friends would describe them. They're really difficult problems. But AI is really coming on. Like it's, we say it's now sort of, I guess, 10, 12 years since the AI Big Bang, when we sort of started to realize that this new capability set would be useful for problems that really matter. And over those years, we've really sort of fine-tuned the methodologies to tackle problems of this complexity and scale. So before we sort of jump in, I did also want to do a shout out to the amazing researchers that you're about to hear from. They've been working, they've come together, they didn't know each other 8 weeks ago. But the magic of FDL is we bring people who really understand the problem domain. They're problem specialists with people who really understand the machine learning domain, so the AI specialists, and we bring them together, and then we support them with a lot of resources from our friends at Google Cloud, NVIDIA, Scan Computers, and Lux Provide. And then you get to this point where we have some really extraordinary state-of-the-art applied AI that no one's ever seen before on these extremely difficult problems. So I'm very excited. I'm going to stop talking now, but just wanted to say thanks so much to the teams for having faith in us. Thanks to ESA for giving us these great problems, and yeah, just can't wait to see the results.
Fantastic. Thanks so much, James. And first up, as a matter of fact, we're going to introduce Nicola Lonzeppa, a senior Earth observation scientist at ESA's Phi Lab. And Nicola today is, well, first of all, of course, you mentioned ESA is a key partner of FDL and has been for since 2018, have been collaboratively working with us to push the boundaries of innovation with regards to Earth observation. And Nicola is going to join us and delve deeper into three transformative areas that are crucial to the integration of Earth observation and AI at ESA. Hybrid observations, which amalgamate multiple data sources for enriched insights, advanced sensors that significantly enhance our observational capabilities, and predictive live twinning simulations, which enable us to model and forecast complex environmental and spatial phenomena with unprecedented accuracy. Nicola, it's always good to see you. Welcome and thank you. Share a little bit with
Thank
us
you,
some of the exciting things you folks have been doing at ESA. B-Lab.
Thanks a lot, Jonathan and James. Very glad to be here today and with you all. I don't know if you are broadcasting the slides now. Can you confirm that?
They are coming up.
Okay,
I can see
thanks.
the team working on that to share that right now. Should just take us a moment. You had some beautiful imagery in there, and
Indeed,
took a little
indeed.
extra time for us to get that ready so we could stream it for you, but it's absolutely worth it. So
Okay, let's wait for a couple of seconds, obviously.
yeah,
Hopefully.
here we go.
Right, perfect.
Perfect.
So next, please, you can move to the next slide. Okay, well, actually, given the many great challenges humanity is facing today, I mean, it's really crucial that we take well-informed decision based upon a thorough understanding of Earth and the impact of human activities. So therefore, it's crucial to have an excellent monitoring system and activities to keep an eye on our blue planet Earth and take it pulse, actually. And actually, this is the essence of what we do in ESA. Next, please. So as you may know, ESA build and operate a set of satellites. For science first, recently, for instance, we launched the EarthScale mission sensing the atmosphere. Soon there will be the biomass mission looking at above ground biomass and forestry. On the other side, we support as well the European Commission on more, let's say, operational mission. As you may know, the Copernicus missions with Sentinel-1, 2, and so on and so forth. And we also support EUMETSAT with meteorological satellite. So as of today, we support up to 14 different satellites and actually many more in preparation, as you can see in that slide. Next, please. So of course, all of these different satellites generate, as has been said before, an unprecedented amount of data to be analyzed. Just talking about Copernicus mission, this represents 16 terabytes of data, high quality data every single day. So this is enormous. So one can easily imagine that advanced processing technique like AI is the perfect tool to process this information. So AI has different advantages. Scalability, because you can process vast amount of data very quickly and efficiently. AI can also automate the data processing pipeline from data ingestion to data analysis without or with limited amount of supervision from the human. AI is also very good and excel at identifying, let's say, unrevealed pattern and do pattern recognition into this big amount of data that we have and also detect anomalies in large data sets. AI, of course, is very good at improving well, the data analysis and improving the data quality that we get from this and we mine from this raw data. And of course, AI can integrate many sources of information, not only sensing imagery from satellites, but also social media or any type of information to provide more comprehensive insight about our blue planet. So at the end, and I think this is also the title that you see here, we are trying to move from a paradigm of Earth observation to Earth action. And AI is very good as well to provide actionable information so that actually decision maker could take the right decision at the right time. Next, please. And yes, thanks. All of that is actually closely related to a concept that we define all together with FDL folks. And the concept is so-called Earth System Predictability, ESP at short. And Philab ESA was very, very happy to support this, the forum that we had last year. ESP is a kind of strategy that integrates Earth observation data with a broad range of like predictive model, simulation into decision-making tools. And ESP is built on of course, the revolution that we see in Earth observation with many satellites, not only from space, not only from, let's say, space agency, but also from private stakeholders, combining with rapid AI-enabled prediction, uncertainty quantification, simulation, digital twin, visualization, which is also very important, LLM and LPA, stuff like that, allowing everyone to understand, experiment, and make at the end some kind of decision based on that. Next, please. So actually, as has been told before, since 2018, I thought it was 2017, but 2018, ESA Philab indeed support this FDL sprint. So as it has been said, this research sprint apply emerging AI techniques to space science. We try to push the frontier what is possible with space data and Earth observation information. So the goal of FDL is not only to develop solution and workflow that can be useful for ESA, but also to useful for any external stakeholder. It could be UNICEF, UNOSAT, UNOSA, and so on and so forth. And also simply to try to do good things. And this actually, it has been an exciting years. And I was delighted to see this 4 selected topic that really build on ESA mission and Copernicus mission. I mean, ranging from the foundation model with Sentinel-1, exploring tomographic SAR with the biomass that will be launched next year, tackling AI and heliophysics with the upcoming Vigil mission, and also last but not least, exploring the atmospheres and cloud with the recently launched EarthCare mission. So all of that was very exciting for ESA, obviously. Next, please. Before to close here, I'd like to thank, of course, all the researchers who did most of the technical and scientific work here. So thanks a lot, kudos to you all. And I hope and trust that this experience was very enriching for you and that you will be able to build upon and capitalize for your career. That is, I guess, will be brilliant. I'm not forgetting as well all the sponsors, support, faculty members, advisors, all the colleagues as well from ESA and Trillium Technology that support this program on behalf of ESA Philab. So thanks again all. Over to you, to Jonathan, for the rest of this showcase. Thanks a lot. See you.
Wonderful. Nicola, thank you so much. And that moving from Earth observation to Earth action is so important. And that really squarely falls into that category of meaningful. I think Catherine's going to put a link in the chat to the Earth Systems Predictability Report that we produced with ESA late last year for people to read more about that very important thing, Earth action, moving to Earth action. So thank you so much for setting that up, and we're going to get started with our researchers. Okay, with that, let's get right into it with our very first team, Lessons from Space for Earth. Very exciting stuff from Alex Levin and Guy Schumann. This is our, the topic really will sort of center on engineering for applied AI, science-driven development for real-world impact. Alex and Guy are going to share insights from their experiences in deploying AI to address real-world issues. They'll delve into the engineering challenges that extend beyond merely crafting effective models, focusing particularly on strategies to ensure systems are reliable and trusted. That word in AI these days, trusted. Guys, welcome, and please share.
Yeah, thank you, Jonathan. I think Delve might be more than we're up for the few minutes that we have, but between the two of us, plenty to share on what reliability means in scientific machine learning and simulation, and the trustworthiness, especially for boots on the ground users and operators making decisions.
Yeah, absolutely. Very happy to join you here, Alex. I mean, this is a very important topic. I mean, if we look at flooding, that's what we do at RSS-Hydro, but also we part of sponsoring the SAR-FM activity for one reason. We want to see a bit more of these challenges addressed, maybe not ML based, because ML is wonderful, it can do great things. We all know that here. This challenge is one of the best ones in tackling these technical challenges. But then the question is, how can you, like you say, boots on the ground, right? How can you make that technology accessible and even, more important, make it understandable by those people, exactly, boots on the ground. If we talk about flood disasters or any other type of disaster, the person actually needing good flood information is the person, if we do search and rescue, everybody understands that here. So how do these people use that new tech, right? This is for me one of the biggest challenges still, and maybe it's part of the FDL challenge to also address that, but here we really more technical, but it would be, so that's one of the challenges for me, is not yet completely solved. I mean, some of us have very good ideas how to do that, but I don't know if you have examples on your fields, but this for me, I mean, disaster taking action.
Yeah, for sure.
Yeah,
and I would say that, like, I mean, just the concepts of good enough and taking action can mean different things with respect to machine learning research, where the action sometimes goes as far as a poster presentation. But what we see, and especially when we're working in areas that definitely in Earth systems, but even plenty of areas of more constrained physics environments, where the action and getting to something that is like a solution for people, like you're saying, the flood information to take action, but a solution in, say, fluid dynamics settings, that is actually several steps beyond the machine learning task, the machine learning view of like what is a solution. And there's much more nuance or downstream variables and noise, confounding information to consider. So then when we kind of dial it back to, all right, so this intelligent algorithm, this sort of inference, this structured data that is representing something that is really, really high dimensional, and I'm a human. I think in linear terms. I need to understand and act on this information. Then we get to this sort of good enough criteria, right? It's like the machine learning model. Be really cool if it solved fluid dynamics. We don't need it to. It needs to be slightly better, but really more like a step change over the existing abilities of modeling tools, in that maybe we can iterate over experiments faster because we're using a machine learned surrogate, or maybe we're able to couple two different physics together, like a fluid structure interaction, when really that coupling happened in the space between my ears as a mechanical engineer, and tried to pass it along to my colleagues. But now we have data-driven tools that can help in those respects, and then pass it along downstream to operators, engineers, other scientists to solve downstream tasks.
I think, it's right. I think, ML doesn't need to solve fluid dynamics, if I take your point there. I think what ML could help us do, if we take a large language model, we could start making the information we produce technically more easily digestible by human beings, and faster as well for helping decision making. So it could be by coupling large language models like ChatGPT or Gemini now that everybody understands and can interact with. I mean, literally anybody can write a text in the form of a question or even speak to it. Coupling those to the more technical ML world for image segmentation, for example, in terms of a flood, I think that would be very powerful. And I know FDL has been trying some of the challenges before. The flood brain is one example. I mean, this was the start of using an LLM-based flood reporting tool. Something like this would definitely be going in the right direction. Absolutely, I think so.
Right.
Well, guys, we're running out of time here. We're like the award ceremonies. The music plays.
Yeah, it's way too exciting.
Just me. I didn't know we were getting played off stage.
Yes. Well, guys, thanks so very much
great.
for chatting a little bit about your adventures in high TRL. TRL is such an important thing for us to think about these days in all the things that we're trying to do in these domains, and I don't think it gets enough attention. So thanks today for bringing that up for us.
Absolutely.
Okay.
Thank you.
Thanks, guys. Next up, we're going to move another team. We're going to move to our 3D clouds team. We're going to hear from Jopo Massant, Stella Gritsu, Lila Fresham, and Emiliano Diaz. Welcome, everyone. What a team you guys have here today. Tell us a little bit about, I mean, aren't clouds 3D to begin with? Tell us a little bit about your research and why we should be caring about the work that you have all been doing. Welcome.
Clouds reflect solar radiation back into space. They also trap infrared radiation emitted under the clouds. Two competing effects that are the biggest source of uncertainty in predictions of our future climate. The radiation balance depends on many factors, including the three-dimensional structures of clouds throughout the atmosphere, which is not easy to measure on a global scale. ESA's and JAXA's new EarthCare mission was successfully launched on the 28th of May 2024 and will use LiDAR, radar, a multispectral imager and a broadband radiometer to assemble a 3D snapshot of the atmosphere along narrow tracks. However, this strip represents only a small fraction of the atmosphere compared to the 2D imagery acquired every day by satellites in geostationary and low Earth orbit. The 3D Clouds team aims to use machine learning and multiple 2D images to reconstruct the three-dimensional cloud structure beyond the narrow tracks, ultimately providing a robust model of our atmosphere over long timescales to better understand our future climate.
Hi, I'm Joppe, and to know why clouds are so important, let's take a look at this rather scary graph of climate change. One thing that really stands out here are these very high uncertainties. To know why that's important, I'm going to quote Nobel Prize-winning psychologist Daniel Kahneman in saying that climate change is so paralyzing because it is a distant problem requiring us to sacrifice now to avoid uncertain losses later on. And this uncertainty really is a key word here. There's something in the climate models that is clouding our vision. And I kind of gave it away here, but clouds heavily impact the climate and they are a major source of uncertainty. Clouds cool the planet by reflecting sunlight, but they also warm the planet by absorbing heat. And as the climate changes, so will this dynamic, which results in high uncertainties. What is really missing from these climate models are real-time 3D global cloud maps. So, how can we get there? Let's take a look at how we currently measure clouds, and luckily we have satellites for that. And a very good example of this is the recent ESA mission EarthCare, which produces these very detailed vertical cloud profiles. As you can see, however, the profiles are very, very narrow, and that can give us a global coverage about every 25 days, which is already very impressive, but can we do better? Could we look at our other friends in the sky for help? There are dozens of satellites imaging the Earth many times a day. What if they could help? What if we could go from a two-dimensional satellite image to predict the vertical cloud profile? And if we could do that, what if we could use the spatial extent of those images to go towards 3D? That was a focus of our challenge. This is what we have been working on for the past 2 months with this amazing team. And what makes us so uniquely positioned to tackle this is the combined expertise in satellite imagery. We have experts in clouds and how they affect the climate, and we have specialists in artificial intelligence. Stella will now cover more about how we tackled this challenge.
Thank you, Joppe. So, the idea of our challenge is to build a model able to go from satellite imagery to 3D cloud maps. And to accomplish that, we have developed NEFOS. But first, let's have a look at what satellite data we have to tackle this challenge and how do we get to this data. On the one hand, we can take advantage of satellites that are in the same track. Here we have a satellite generating cloud profiles, and in front of it we have another satellite delivering 2D images at the same time. The combination of these data sources is really powerful on training AI models. On top of that, and in order to go towards real-time maps, we can take advantage of satellites which are always measuring the same place on Earth, but at very high temporal resolution, every 15 minutes. This could allow us to generate 3D cloud maps in real time and also explore cloud dynamics and evolution. So, how can we leverage this data to train machine learning models? As a first step, we align this diverse data in space and time and create unified 3D representations. This enables the models to learn the relationships between images and the cloud profiles, but also generate 3D outputs. The next step is then to actually train AI models to go from these 2D images to this profile reconstruction in a 3D cube. So let's delve a bit deeper into what our learning strategy looks like. We start by basing ourselves on a state-of-the-art neural network architecture, the so-called UNet, which has been proven to be very powerful on reconstructing 2D images and 3D shapes. And if we have a look on how well it does, we can see that after even 1 hour of training, it's already learning the altitude of clouds and the very vague patterns of whether it's cloudy or not. And after some more extensive training, it's going closer to what we actually want, the real cloud profile measured by the satellite. And now Emiliano will talk about how we further push this state-of-the-art model.
Thank you, Stella. So how do we improve upon this state-of-the-art result? The bottom line is to use more data. Along the satellite tracks, we have satellite imagery and vertical profiles, which can be used to answer the question, if a cloud has a given spatial pattern, what does its vertical profile look like? For this, we have gigabytes of image profile pairs that can be used to train AI models. Off track, we have only satellite images. These could potentially be used to learn more generally about cloud behavior. In this case, we have much more data, in the order of 1,000 times more. So how can we combine the small specialized dataset and the large general purpose dataset in order to get high quality 3D cloud maps? Our NEFOS methodology is a two-step approach where, in a first so-called pre-training step, we use the large dataset of satellite imagery to learn generally about cloud behavior. And in a second so-called fine-tuning step, we use the smaller dataset to specialize the model's knowledge of what a cloud's vertical profile is based on its spatial pattern. In the first pre-training step, using the large dataset, we develop a model that learns general cloud behavior by using the self-supervision trick. This trick involves pairing each image in our large dataset with a masked version of itself. The AI model is then tasked with reconstructing the original image from the masked version. To do so, it is forced to learn deep universal properties of cloud behavior. In the second fine-tuning step, we switch out part of our AI model with the new version specialized in 3D cloud reconstruction and train it with our small dataset. The final AI model uses information learned from the large dataset in yellow and from the small one in blue. As for the results, on the left we see a cloud image, and on the right we see vertical cloud profiles where the top panel shows previous state-of-the-art vertical profile reconstruction. The middle panel, our model's vertical profile reconstruction, and finally, the bottom, the measured vertical profile. We can see that our model recovers a sharper, more accurate reconstruction. Now Lily will talk to you about what our work will enable for the scientific community.
Thank you, Emiliano. So in addition to predicting the actual vertical measurements taken by the satellite, we used our models to directly reconstruct key quantities that scientists are interested in. In this example, a model predicts whether an area is clear sky or cloudy and identifies the cloud type. This enables us to validate our model using vertical measurements of cloud types from satellites as well as ground-based sensors. Here we can see that our model accurately reconstructs high clouds and even correctly detects some clouds that are covered by thin cloud shields. So we've been talking about 3D clouds, and so far have been showing two-dimensional vertical profiles of our predictions that are looking better and better. But wait, there's more. While the cloud profiles are these thin vertical slices, our model directly predicts clouds in 3 dimensions. It learned to reconstruct a 3D cube of clouds from satellite images via training on 2D profiles. Here you can see one example of such a 3-dimensional reconstruction from our model. With Nephis, we can increase the extent of vertical cloud data spatially, a key step towards creating global 3D cloud maps. And not only that, since our model was trained to predict clouds from geostationary satellite images, which are available every 15 minutes, we can make continuous time reconstructions of clouds using a series of satellite images as inputs. We have thereby extended vertical cloud data in both space and time. To summarize, what does Nephis enable? We built a modular satellite data processing pipeline that can be used for future Earth observation projects. Our model uses global satellite data, which is publicly available near real time. By providing our models and data processing tools to the public, we enable anyone to create 3D cloud maps at any time for anywhere on the globe. Our modular tools, which are trained on previous satellite missions, can easily be adapted to learn from EarthCare's higher quality data once it is available to make even better predictions. So with Nephis, we provide a 3D cloud reconstruction tool that the community can build upon in the future. This project brings us closer to obtaining 3D real-time cloud data, which will enable scientists to study the behavior of clouds better than ever before, and has the potential to advance climate science and improve climate models. This will make climate projections more accurate and bring the scientific community one step closer towards solving the climate puzzle. Thank you very much.
Thanks, team. It's hard to not use adjectives to describe how good your work is, because you want it just to speak for itself, and it does, but we can't help but say words like incredible, awesome, impressive. So well done, and congratulations on some absolutely fine work, 3D Clouds team. For those of you who want to know more, Josip has posted the link in the chat, so you can find out more about their very, very impressive and awesome and incredible work. Next up, we're going to hear from our Biomass SAR team, SAR, S-A-R, Synthetic Aperture Radar. So right after the introduction video, the Biomass SAR team, that'll be Grace Colvard, Laura Shuda, and Junpei Takima.
Forests are some of the most precious and diverse ecosystems on the planet, with tropical forests hosting around half of all known species. Forests also store enormous amounts of carbon, locked away in trunks and branches as biomass. It is essential that we measure the volume and health of our forests worldwide and continue to update our knowledge as our climate changes. In 2025, ESA will launch the Biomass mission, equipped with a world-first orbital P-band synthetic aperture radar instrument to continually map our forests on a planetary scale. The FDL Europe team this year have developed new machine learning workflows that rapidly produce accurate maps of forest structure in 3 dimensions, leading to trusted measurements of our forest ecosystem over time.
Hello everyone, and welcome to the Biomass SAR team presentation. Hello everyone, welcome to the Biomass SAR team's presentation. My name's Grace. I'm really excited to share with you the results of our 8-week research sprint. As Klaus mentioned, our team was heavily inspired by the ESA biomass mission that you just heard about, and it's hoped that the result of our project will help to shape some of the data products that might come out of this satellite. The Biomass SAR team is made up of 3 researchers, myself, Grace, Laura and Junpei, and our 2 faculty, Joseph and Carol. I'll start by giving you some background to the challenge before handing over to Junpei and Laura, who will talk about our results. I'd like to start by asking you to take a moment to listen to this sound and think about what you hear. You are listening to the sound of a tree. This is the sound of water moving inside of a tree trunk. These sounds are captured using stethoscopes, such as demonstrated by the lovely Judy Dench here. And we thought these sounds were a really lovely example, that a reminder that trees are alive, they are organic matter, they're a form of biomass. And this biomass is primarily stored in forests around the world. Forests are home to millions and millions of plants and animals, with over 60,000 tree species across the world, as well as playing a vital role in the carbon cycle. It is estimated that if forests were allowed to grow and mature strategically, they could increase this carbon drawdown potential to over 200 billion tons of carbon. Protecting forests, supporting carbon removal, protecting habitats of communities around the world, these are such important challenges. And understanding the makeup of forests in terms of tree species can help with biodiversity mapping and tracking the health and resilience of forests over time. So how can we protect them? Historically, satellite data is a really common tool that's been used to track changes to forests over time due to its low cost and global coverage. Historically, this has typically been overhead visual imagery that's been used. However, overhead visual imagery cannot tell you what's going on beneath the canopy. Hence, our project and the ESA Biomass satellite will be using synthetic aperture radar data, or SAR data. SAR data is a longer wavelength radiation that can penetrate the upper forest canopy, as well as being an all-weather imaging system that is not limited by clouds. Leading to our team challenge, using SAR data products to predict forest biophysical parameters. There are two data products that we use in our challenge. The first is a kind of 2D SAR image called a single look complex image. The second is a 3D tomographic reconstruction. You're going to hear the word tomographic quite a lot in this presentation. A tomographic cube is a data product that is derived by stacking multiple SAR images, all taken at slightly different angles, and applying a whole lot of processing to create a 3D reconstruction of the scene. These data products can be captured either by satellite or via an airborne imaging system like a plane or a drone. So obviously the ESA Biomass satellite will be a satellite, but a lot of the data that we're using to kind of prepare for the satellite launch is captured via plane. And now I'll hand over to Junpei, who'll tell you a bit more about the satellite and more detail about our challenge.
Thank you, Grace. The European Space Agency will launch a new SAR satellite biomass mission, which will be the first P-band sensor satellite. This mission aims to measure forest biomass globally, playing a crucial role in monitoring carbon flux, enhancing the climate change modeling, and supporting forest management. The satellite will bring SLC data, which will be processed using tomographic SAR analysis to generate 3D data, which we have utilized in this challenge. Challenge is based on a dataset from diverse forests within the Eiffel Park in Germany, dominated by beech, oak, and aspen trees. The necessary dataset was collected using airborne P-band SAR and also LiDAR. LiDAR means airborne laser data, which are remote sensing technologies. By using this airborne dataset, our challenge aims to provide deeper insights into the satellite biomass mission. The provided dataset include training dataset such as tomographic cube, data intensity, and also stack of SLC data, which Grace explained. For ground truth data, we utilize tree height information obtained from LiDAR and also the tree species map taken by field surveys. We have utilized three key challenges: tree height estimation, using intensity image as training data, and tree height information as ground truth, we predict the tree height. And second one is a tree species classification. Here, we used intensity image for training data and tree species information as ground truth data to predict tree species. The third one is a 3D reconstruction. We utilize SLC data as a training dataset and tree height information as ground truth data to predict tree height. This is our machine learning pipeline. A detailed breakdown will be you can check in the tech memo. In briefly speaking, we just split dataset, applied machine learning models, and estimated both tree height and species. And you know what? Even with these three difficult challenges with hard data, we managed to tackle each one. From the next slide, Laura will explain about our results. Over to you, Laura.
Thanks, Junpei. I'm now going to show you our classification model results. In the moving image, you're able to see the different dominant tree species in different colors as results of our model, combined with our height estimation. For the classification model, we obtain an overall accuracy of 75%, which is quite good considering that we're estimating 8 different classes of forests. The model performs better on certain species of trees than others due to data availability. We're now going to show you the results for our height estimation model. We ran the model for each forest type, and you can see that the errors that we get for each class differ based on the data availability. But we still get an overall mean absolute error of about 1.5 meters, with most trees being around 20 meters high. The right bottom map shows the ground truth and the prediction results, and you can see that there is a very good match. The final part of our challenge was to work with the SAR images directly to see if we could recreate the forest heights without the tomographic processing. Our initial results show that high reconstruction is possible, although the high prediction is less accurate than using the tomographic data directly. Given our results, our project will benefit the community for a number of reasons. One of those being the availability of processed data and translated scripts. We have processed classification data through data extraction, LiDAR data through converting between coordinate systems, and Sentinel-2 data through image alignment. The second reason is that we will make available our state-of-the-art models for the classification, height estimation, and tomographic reconstruction. The results that we presented are also very exciting because of the real-world possibility to support the ESA biomass mission, and also for their potential to be generalized on wider set of data to generate a global biodiversity map. Also, if integrated with time series data, our models have the potential to support forest monitoring and also disaster response. We would like to thank our partners and give a specific shout out to Klaus and Francisco for all their invaluable support during this project. And thank you so much for listening and for caring about our forests.
I think everybody wants to go out and listen to trees now. And this definitely also falls into the category of meaningful because, of course, if we're going to really understand Earth systems and what's going on, we need to know what is there and what we have to work with and what is changing. So this is phenomenal work towards that goal. Thank you so much, Biomass SAR team. I was looking forward to seeing more people taking the models that you make available and also amplifying the work that you have done so far. Next up, we're going to do a panel. We're going to do a climate resilience panel with a handful of our partners and researchers. So if we could bring up to the stage, Nicola, Kelsey, Devas, Margarita, Giuseppe, William, Carol, and Joseph. Might get a little crowded up here, but not to worry, we have plenty of room for everybody. Our panel is going to offer insights on research challenges and the impacts discussed in the presentation that we just heard, and they're going to focus on their areas of expertise. They'll explore why these issues matter, what makes them exciting, and the potential opportunities that they unlock. Who'd like to jump in first? Don't be shy.
Okay, so I wanted to just to start. So biomass estimation is a powerful tool for measuring carbon stocks, as you have seen, and enhancing disaster resolve efforts. So our team successfully tackled 3 challenging thought machine learning involving complex datasets this year. The results are promising and offer a solid foundation for future teams to build upon. The potential of upcoming biomass mission is truly exciting. With additional data, we will be able to develop a global machine learning model to estimate biomass more accurately. These models, while powerful, can produce erroneous and biased estimates. To ensure ethical integrity, it's crucial to develop anomaly detection methods alongside them and perform continuous analysis.
Super. Other thoughts on the presentation that we just saw and why this matters, why we should be paying attention, and how these technologies are contributing to climate change mitigation and our sustainability efforts?
Yeah, I think for me, something that's really exciting about these projects is the concept of global solutions, particularly when we think about how traditionally underserved communities that perhaps don't have their own sort of data infrastructure to do these types of mapping. Survey methods are really, really expensive. So it's really exciting to see being able to use space-based assets to support this kind of global initiative when we think about the communities that are going to be most impacted by climate change. So I'm really excited to see these results, and it's really going to be groundbreaking for these different communities.
Excellent. Yeah, real impact on data collection and accessibility to it all. Other thoughts on Biomass SAR?
Well, I believe that overall these presented advancements in both teams that just presented contribute for more precise, informed, and effective climate action on a more global scale. We are aiming at having models that contribute to the interventions to be both more impactful and equitable, and it can help also support sustainable management of the resources and the trade-offs between services. So these are great tools that are being made available for developing further downstream tasks here. I think it's very important.
Thanks, Carol. Okay. Yeah. Margarita, William, you're nodding your heads. You're in agreement. Do you have something else that you'd like to add to that?
I'm in agreement. I would like to talk a bit about the 3D cloud side. And,
sure.
And I wanted just to resonate with Joseph, like in general, and say that I'm so proud of the team's achievements. And like, it's impressive how much you can accomplish in such a short period of time. And it's all like through like collaboration and by helping each other. And as for the results that you asked about, the 3D clouds have created a modular pipeline that not only delivers a valuable 3D dataset to the community, which is important, but also allows us to be able to immediately like work on EarthCare's data as soon as it's available. So I feel like this is just the beginning for this project and for most of the projects, and like that's what I feel, and I'm very excited about it.
Super. Super.
Yes, I think to build on that, and again, I'm in complete agreement, and something that came to mind listening to both the clouds and the biomass presentation is that both have this theme around these latest ESA satellite missions, Biomass and EarthCare, which are providing fantastic, never seen before data for analyzing climate change, but we can't wait a decade to collect data from just these satellites to make, informed decisions. And I think a big strength from both projects is this use of data fusion to make use of all the legacy data and legacy satellite observations we have from decades, to combine those with the high quality data that allow us to make not only critical insight into climate change, but also timely insight.
Wonderful. Giuseppe, anything from you on 3D clouds?
For sure, I wanted to build on what my colleagues had previously mentioned, especially when it comes to we're looking at the challenge of the data not necessarily being there. Beyond we're talking about things like the quantity and stuff, that this is actually a fairly challenging machine learning problem, because if you look at the other types of 3D reconstruction problems, you usually have some kind of ground truth for your 3D. But in the case of the clouds, especially, you really only have two distinct views. And so really kudos to the team for being able to rise to that particular challenge, for being able to, as well as alluding there's a certain sense of fusion from these different sensors, from being able to use the views that we do have in creative ways. The team did a really great job.
Excellent work. Divas. Oh, go ahead, William, please.
No, yeah, if I can add on that, I think the
Of course.
strategy put in
Nicola.
place by the aerosol and 3D team was great. I mean, doing self-supervised learning with unpaired data set and then doing this kind of specialization of fine-tuning with paired data is just to the state of the art is great and very timely, because we see that this kind of strategy for foundation model, so it's really up to date, and I'm very proud of the strategy indeed that was put by the teams to tackle this lack of data and reference information and stuff like that. So well done, kudos.
Nice, thanks, Nicola.
I wanted to add,
Yes.
just wow, congratulations, thank you for the amazing presentations, both projects really amazing. And yeah, just to resonate and maybe highlight some of the key takeaways for me, at least. Yeah, the use of multi-source data, it's really crucial. And I think both projects have shown this. And as part also the discussion, how do we make these things actionable? So connecting also to the boots on ground, or this, we really, I look forward to these things being used and having an impact, so reaching out to the local communities, local governments, so that they can really take advantage of these insights and take action. And doing this open sourcing that you've shown and you've done, this is the right way forward. So kudos to you all for this work.
And of course, open source is one of the answers to the question I'm about to throw out to you all right now, and feel free, anyone, to jump in. What are the ethical implications? Ethics is more and more coming up as something that we really have to talk about when we're talking about using state-of-the-art technologies like this. What are the ethical implications of using AI in climate action? How do we, beyond open source, how do we take and make sure we have trusted AI-driven solutions and make sure they're equitable and do benefit all communities around the world? What are your thoughts on that? Anyone, jump in.
I can say something here. So as I was alluding to, there's this, especially with regards to the 3D clouds reconstruction, there is some uncertainty when it comes to how the problem itself is posed. And so you're basically solving an inverse problem where not all of your observations are there. And so one of the things that we really have to focus on is being able to quantify our uncertainty of those predictions. There's especially, if you have a casual perusal of machine learning, you tend to think that, oh, these are very confident predictions. The machines can be very decisive, but very far from that. We need to be, hyper aware that sometimes what these models are producing should be scrutinized.
Nice. Other thoughts?
Yeah, I think it's particularly important as well to communicate what uncertainty actually means, especially to kind of echo what Devis mentioned about communicating with local stakeholders, governments, policymakers, folks that are very far away from the technical solution in terms of their technical expertise and their background, but ultimately the folks that are going to be implementing solutions that are going to impact their communities. So communicating, I think, what uncertainty actually means, confidence intervals, prediction boundaries, these types of things will be really critical to ensure that they can be adopted when you're thinking about forming technical solutions into policy. So I feel like it's not to be understated the value of effectively communicating your results and kind of breaking it down into terms that across the board, regardless of your technical expertise, you can kind of digest and understand what that means. And then using these AI solutions kind of in partnership with existing kind of survey methods or existing policies that are already kind of going on in these communities is critical too. Not trying to come in and say AI is the solution to everything, but rather AI can help us for the solutions that we're looking for these different climate problems.
Yeah, really good point. Technology won't solve our problems, but we won't solve our problems without technology, right? That old mantra there. Thank you. Good point. And then finally, just anybody else?
I just wanted to add to resonate with everyone. And yeah, for instance, in biomass, you can use this information for really bad decisions. Maybe you can cut certain type of tree and just search for that type of trees. So I think that, as the other has said, we have to have some policies just to increase our awareness of the biomass. And I think that biomass estimation is a really good thing, but yeah, there are some open questions that we have to solve in the future.
Great way to end. Well, that's our wrap-up music. Time to move on. Thank you all for joining us here today for this brief panel on climate resilience and AI. And we're going to continue now with our next research team. So next up, we're going to hear from Andrei Krutsilov, and we're going to hear from Kartik Varnislavam, and we're going to hear about SAR-FM, synthetic aperture radar FM.
Space technologies are delivering greater value to a more diverse set of stakeholders than ever before. Earth observation data especially can deliver great value in diverse applications such as environmental monitoring, critical infrastructure surveillance, flood mapping, or maritime surveillance. Numerous Luxembourg-based space players are using EO data in their business models for these purposes. In addition, the use of machine learning foundation models are gaining traction in the remote sensing community, thanks to their adaptability and generalization potential. These models could be a game changer, particularly for synthetic aperture radar data users, as the complexity of SAR makes it difficult to apply analytical processes consistently across different locations and times. Building on their work from 2023, the FDL Europe Challenge aims to further refine the best practices in constructing such a scientific SAR foundation model. It is anticipated to have a substantial impact, unlocking numerous applications, particularly in nighttime, in areas obscured by clouds, and to assess the impact during natural disasters such as flooding. Hence, the Luxembourg Space Agency is more than happy to support this challenge together with Luxembourgish partners Lux Provide and RSS-Hydro.
Hello everyone, we are a SAR-FM team. Let's explore what we did for our 8-week FDL challenge. Our team made up of two researchers. I am Kartik and Andrei. We both are ML experts. Then we have an excellent faculty, Guy, expert in hydrology, and Freddie and Raul, both are ML experts, as well as Earth observation experts. What is a SAR? It is a synthetic aperture radar. It's an active sensor. It transmits and receives microwave signals. It can work day or night at any weather. It is a perfect for Earth observation. The traditional machine learning models used for Earth observation, it requires large amount of label data. And these task-specific machine learning models don't generalize well on SAR data to different geographical regions. In this example, the models trained on Puerto Rico, not generalized well on Cairo. Yes, the foundation models may provide a solution for this. But what is a foundation model? The foundation models are a new class of AI. It is trained on a large set of unlabeled data in a self-supervised manner, where a large pre-trained model encodes information as a lattice representation called embedding. These foundation models can be quickly and computationally in economical manner adapted to various use cases. In this project, we aim to evaluate their potential of the challenge relevant to Luxembourg flooding. This accurate map of Luxembourg flooding are critical for supporting relief and recovery. So the SAR data is ideal for this sort of mappings. The foundation models are being developed by NASA, CLAY, and FDL. And there are many others. How can we efficiently choose the best foundation model for a range of use cases? We have built a new toolbox and dataset to assess this foundation model for a set of given tasks. The Maestro is used for assess the foundation models, and we have used the Maestro to choose the best foundation model for mapping floods in Luxembourg. That leads to a new world-first SAR dataset. As I said, Maestro assess the foundation models by using technique called probing. We generate the embeddings from various foundation models using Earth observation dataset. This generated embedding is sensible to various use cases like predicting tree cover, permanent water, and built environment, as well as various geolocation. Our toolbox Maestro identify the best foundation model for your use case based on the results generated from these embeddings. Why this toolbox is needed? Because Earth observation foundation model is not like large language models. The large language model we will use day by day, it's a ChatGPT, uses this simple textual data as the input is very, very simple. But our case, the Earth observation foundation model uses the complex input data, which are multimodal and image cubes. I said many times, embeddings, what's really is embedding? It is a compressed representation of input data. In an embedding space, the same object live together like chicken and cats, and different objects like apple and chicken are far apart. Let's see an example. We pass this Sentinel-1 image to a foundation model to generate embeddings. This foundation model doesn't aware of our use case. Our use case here is prediction of water and land. And these are these embedding generated from the foundation model. The foundation model generated embedding, it can easily distinguish between water and land. So this shows us the embedding contains a meaningful information of Earth observation data. To assess these embeddings, we used various probes. The two important ones are linear probe and segmentation probe. The linear probe can estimate total amount of percentage some object present in this image, like total percentage of trees in a given image. Likewise, segmentation probe tell us where the thing is located in the image, like tree segmentation. Andrew will walk us through our experiments and results of Maestro and Welfare SAR.
Yeah, hi everyone. So yeah, we did a few amazing things. As Katak said, we have developed a set of tools to make computationally cheap but effective probes that allow us to find an optimal foundation model. And optimal means that model might differ depending on the architecture, on geography, other stuff. And in this figure, you can see that how simple linear regression, most primitive in our model, applied to the embeddings produced by the corresponding model can estimate which foundation model would most likely be the best for a given task of predicting, in that case, the percentage of built environment on satellite image. Yeah, so we can also suggest which training data should be used for downstream tasks, for example, permanent water detection. Specifically in Colombia, it is important to understand that, we need to find some alternative to replace the data in Colombia because there is not much data about Colombia. So using Maestro Toolkit, we can find an answer, and Maestro providing us with answers that we should use clay with Sentinel-1 data from the United States. Now, this is a segmentation probe. And this segmentation task is much more complicated and requires a lot of experimentation. But we found that the best practices could be achieved. As you can see on this slide, there are embeddings extracted from the same foundation model with quite different results on the left and right. And we should be careful of what we're doing. The second huge deliverable is our VOD SAR dataset and the model, which is a continuation of last year FDL, but we changed the modality from optical to SAR, obviously. We collected new data, proposed brand new model. The data set consists of several flood events, and for each image, we have Sentinel-1 images before and after the flood event, and of course, the flood mask. So this data set, the foundation model selected by Maestro, and segmentation probe output together formed a new flood detection model that we tested on more than 2,700 image files of the Luxembourg flood event of 2021. As you can see, the results are fantastic. Note that cloud that covers a part of S2 image, it is a big problem, but for our model, it is no longer an obstacle because we are using SAR data, that was all about. And yeah, we are using Sentinel-1 images to do that. So our future work, and as our contribution to the community, we will release the full data set, all data that we used for experiments. It's more than 10 million images or 20 terabytes of data. This is triplets of Sentinel-1, Sentinel-2, and ESA word cover labels. This data set contains seasonal data. It collected for the whole world, so it could be really useful for running our probes and generalized well for different regions. Finally, we have performed more than 2,000 experiments in 35 testing regions. We used 8 state-of-the-art foundation models from NASA, Clay, BiggerSNAP, and of course FDL. We also built a segmentation probe of Maestro based on a wonderful library called Segmentation Models PyTorch, which allowed us to use more than 500 encoders, 9 segmentation decoders for those experiments. And as for word floods, it is a well-polished data set consistent with 12,000 images, including the Luxembourg. Yeah, it is an end-to-end pipeline with 8 currently foundation models that we can use for flood mapping, among other things. Finally, yes, our future work would be to add even more foundation models, state-of-the-art for Earth observation, maybe from some other directions. We would add even cheaper probes to define which foundation model could be used for your specific downstream task. We plan to utilize state-of-the-art segment any change approach from Facebook. It's very good, I think. And of course, we had some success with one-shot learning for regression task, and now we are doing it for segmentation task as well, which is very challenging technical thing, scientific even, not just engineering. So yeah, thank you very much. Thank you for your time. We can hear you, Jonathan.
Oh, Can we hear now?
Yeah.
Oh, there we go. I just spoke too soon. It's always incredible when we see and hear about such exceptional state-of-the-art work. That really is. Thank you so much for that. And it's additionally amplified, that excitement and hope, when we hear that you're already thinking about your future work. So thank you, team SAR-FM, for that presentation and the work that you've been doing. Great. Next up, we have one more team presentation, and then we're going to do one more panel before we do something a little more fun at the end. So if you will, please welcome Team Vigil 2.0.
The activity on our nearest star is increasing as we approach the maximum in its 11-year cycle. We are seeing more sunspots, flares, and coronal mass ejections that can affect the Earth, leading to spectacular aurora like those seen worldwide in early June 2024. But solar weather can also be dangerous, causing power surges in electrical power grids, damaging satellites through particle bombardment, and exposing pilots and astronauts to high doses of radiation. We need better solar weather forecasts and better warning systems. The upcoming ESA Vigil mission to the 5th Lagrange point will provide an unprecedented early view of the Sun before it rotates towards the Earth. This year, the FDL solar eruptions team is providing an early warning system for predicting solar eruptions based on a combination of multimodal data from solar observing satellites, including Vigil. This work has the potential to fundamentally improve the capabilities of our space weather forecasting system for the benefit of the entire planet.
Hello everyone, my name is Aishwarya. Today we're sharing the results of our 8-week sprint on solar eruption forecasting. Imagine predicting a solar storm before it disrupts our technology and lives. Our research is making this a reality, and so the solar eruption team is dedicated to protecting our world from these cosmic events. Let me introduce our research team. We have Hannah, Dominika, myself Aishwarya, and Vexen, supported by our faculty Philippe, Daniele, Giacomo, and Martin. Our interdisciplinary team brings together expertise in machine learning and heliophysics which is crucial in tackling our challenge. Let's dive into our challenge. So here's a brief clip on solar flares and CMEs. As it plays, I will explain a few definitions. A solar flare is an intense burst of light from the sun, and a CME, also known as a coronal mass ejection, is a massive cloud of charged particles. Now, why should we care? As we approach solar maximum, the peak of the sun's 11-year cycle, solar flares and CMEs will become more frequent. These events create awe-inspiring auroras and can also cause significant disruptions on Earth. For instance, solar flares and CMEs from last May led to flight diversions. Now, imagine an even stronger flare hitting us when the sun is directly facing Earth. The potential impact could be significant. Predicting solar flares is crucial. Accurate forecasts can protect astronauts from radiation, reduce exposure for airline crew and passengers near the poles, minimize GPS and navigation errors, inform decision makers to safeguard power infrastructure and prevent blackouts. A major solar storm could cost the US between 0.6 and 2.6 trillion US dollars, impacting hospitals, transport, and daily life. With our reliance on mobile phones and computers, maintaining connectivity is essential. That's why our team works to forecast these events and protect our technology and infrastructure. So solar flare prediction faces several challenges. First, the science behind the sun's behavior is complex. For example, these two images of the sun at different frequencies on the same day provide varying information and look different. We also notice more structure on the sun on the right there. Second, flare events don't happen often, creating a sample bias. This X-ray flux data highlights the difficulty in predicting X and M class flares, which are two classes that are more intense and rare due to the scarcity of data. This underscores the challenge posed by the rarity of these stronger flares, basically. Third, sun measurements are limited. While satellites monitor the sun, they don't always provide frequent measurements from optimal positions. This astronaut image shows why, and we can't send astronauts close to the sun to monitor it, as they would be exposed to dangerous levels of radiation and heat. Now, I'll pass the virtual mic to Hannah to talk about her solution.
Thank you, Aishwarya, for highlighting why flare prediction is such a difficult task. My name is Hannah, and I'm going to talk about how Vigil can help. This video illustrates the unique vantage point of the Vigil mission. Vigil's position offers us a side view of the sun, a perspective that has previously only been possible when another spacecraft happened to be in the right place at the right time. This optimal position allows us to observe solar activities before they rotate into the Earth's field of view. As you see, Vigil will play a huge role in improving space weather forecast, and we need to start preparing now to use it to its full potential. That's why we need to answer 3 key questions throughout this project. The first question is, are there any hidden correlations in the data in which we can find potential precursors of solar flares? Answering this question will inform the instrument choice of the follow-up mission Vigil 2. Our second question is, can we increase the lead time of solar flare prediction? Early predictions have previously been limited by the sun's rotation. More precisely, we were just not able to see the part of the sun that would be facing us in a few days. Having Vigil, we will be able to observe an active region 5 days in advance, allowing us to extend the lead time significantly. The third question is, can we increase the accuracy of solar flare predictions? The state-of-the-art can only tell us if there will be a flare at any point in the next 24 hours. Additionally, even though scientists have been trying to solve this problem for decades, accuracy is still a big issue. In order to help mitigate the effects of solar flares, we need to be confident in the predictions we make. Imagine switching off our infrastructures just to find that it was a false alarm. So how do we answer these questions? We propose our modular framework for solar flare prediction that we call HelioWatch. HelioWatch allows us to efficiently experiment with the 3 different factors that affect our predictions: the input, the model itself, and the labels we're providing our models with. Solar flare prediction can be based on different types of input data. Useful information is, for example, contained in magnetograms or EUV images showing different wavelengths of light. In terms of models, the machine learning community has provided us with a jungle of different solutions. Finding the one most suitable for this task is a challenge in itself. Last but not least, choosing the labels, which might seem straightforward at first, is actually one of the most challenging aspects. Compared to typical machine learning problems, we have a limited amount of data. This issue significantly increases the importance of finding the best way to formulate meaningful labels. All of this leaves us with a lot of experiments to run. And I'll now hand over to Faxen to show you how HelioWatch makes this possible.
Thank you, Hannah. Hi, everyone. I'm Faxen. Now I'm going to present you a demo of our results. We have developed a pipeline that is able to take in various different data sources as an input. On top of that, we can also plug in different models for training. Essentially, there are 3 outputs that we can learn out of our pipeline. The most informing inputs, the lead time in hours, and the accuracy of our predictions compared to other baselines and true values. So we are not only developing more reliable forecasting models, we are also gaining deeper insights into the fundamental physics of the sun's behavior. Here, we are going to speak about some setup for one of our experiments. For illustration purpose here, this is part of our data preparation. A star denotes a flare. All the circles are the sun images. When they're in white, it means that they have been labeled as no flare, and in blue, the label is flare. Taking the standard approach in the community, we label the sun images which are 24 hours before the flare with the label flare, and proceed similarly for the next flares in the given period of time. We've experimented with various inputs and used the model called ResNet50 to predict whether a flare will happen within the next 24 hours. ResNet50 is a neural network commonly used for visual applications. Here are some initial results from this experiment for a lead time of 24 hours. In line with expectations, we find that the most relevant precursor to solar flares can be found in magnetograms. Here you can see the 3 components of the sun's magnetic field, and the star represents the location from where a flare is launched. In this plot at the bottom, it shows how the true label changes with respect to the dates. 0 means no flare, and 1 means flare. Following the standard practice, as I mentioned before, the label is as well 1 for 24 hours before the actual flare. Stars denote the flares. The vertical dashed line shows the time at which the magnetogram images above were taken. And now we compare our predictions in blue. We show our prediction accuracy in terms of probability. We can see that from October 19 to 20, our prediction in blue rises as we approach the actual flare, denoted by the first star. For the second and third stars, which indicate the other flares, the model has accurately predicted even up to a day in advance. These initial results have provided us a lot of insights, and certainly there is still room to improve. Now, for future plans, I'll hand it over to Dominika.
Thank you, Faxen. My name is Dominika, and as it's been mentioned, we've only just scratched the surface of what our pipeline is capable of offering. Our work so far has laid a solid foundation for what's next, and our future plans include building upon our current outputs and lessons learned. Through the project, we realized that labeling can be a big problem. Predicting flares is complex because they are rare and often happen in groups. So far, we've experimented with the labeling method used by the heliophysics community, but we have a couple of ideas for different approaches. While it would be a paradigm shift, we believe that could help the model predict more accurately. Additionally, so far we've only run models with input from one viewpoint, so we plan to investigate data fusion, and the modular pipeline we set up allows for that. Finally, in the next couple of weeks, we aim to investigate more combinations of the pipeline setup to increase prediction accuracy and gain insights into the underlying solar physics. We believe that if we increase the prediction lead time and accuracy with just one viewpoint, we can create a solution that could potentially be run on board of a satellite. To recap, why does it matter so much? Throughout history, we have seen that solar storms can wipe out telegraph systems worldwide, cause power grids to fail, leaving millions of people without electricity, and cause satellite failures. Now we are becoming even more dependent on our electronics. Moreover, we plan to create a lunar gateway and a lunar base, and both of which would be hugely vulnerable to the effects of CMEs in terms of the electronic failures, but also astronauts' radiation exposure. Thus, we need a system that will tell us when a flare risk is high and when to take action, such as turning off our power grids or shielding inside the lunar base. Fortunately, with the upcoming Vigil mission and the HelioWatch, we are getting closer to addressing these challenges. Thank you so much for listening.
Team Vigil, thank you so much for sharing the work that you have done. Another example of research that falls squarely into that category of meaningful. We appreciate everything you've done over the last 8 weeks at FDL. Great. Well, up next, we're going to do one more panel before we move to something a bit fun. This particular panel, we're going to welcome to the stage, all the folks that you see here right now: Adi, Simon, Kelsey, Gabriel, Martin, Jakob, Mo, Danielle, Freddie, and Raul. And we're going to talk a little bit about AI for disaster response, offering insights onto the research challenges and impacts that have been discussed in the presentation we just heard. They're going to focus on their area of expertise and explore why these issues matter, what makes them exciting, and, as always, the potential opportunities that they unlock. So who'd like to jump in and start off today with us to talk about how these projects are enhancing current AI technologies and the intersection with disaster response?
I can start, Jonathan. Hi, everyone. What wonderful couple of talks. It's amazing to see how much can be achieved in such a narrow amount of time. I'll start with the first one, looking at floods. I come from a space where we are thinking that because of climate change, no matter where you are, there's going to be increasing amount of floods, more severe floods. And the scale of the challenge can only be matched with technology. And the amount of data coming in from satellites and on-ground sensors increasing. So looking at the team who has tackled, there's going to be lots of models out there. How do you make sense of it in a quick enough and compute efficient way was really pleasing to see. And I also mentioned that legacy data set, what was it, 20 terabytes of data? That's going to mean a lot, not just in the emergency management space, but imagine all the things that can be done with that data set. So amazing work. For the solar observation folks, June 2024, it told us, the risk that's out there. Here down in Australia, we were beneficiaries of those aurora rights, but it reminded the community, as they pointed out with their final slides, right, is we are more sensitive to this risk than ever in human history. And we need to be ahead of the game. So what you've achieved again in this narrow window, this sprint, shows so much potential ahead. Really amazing.
Excellent. Thank you, Adi. Who else would like to chime in on this particular topic?
So I think, as Adi said, it's going to be very, very important to build these frameworks that can offer possibilities of benchmarking models, but also of ingesting different data from different sources. And in this sense, I think that the Vigil team, but FDL in general, is kind of paving the way to start building these frameworks and start having data fusion made properly with data that are very heterogeneous.
Thank you, Giacomo. Anyone else?
I think there's an excitement coming our way as we begin to operationalize these systems. And I think the challenge for us is, as everyone's been stretching towards, how do you do this quickly? How can you get it trusted by those who are actually going to make use of it so that they do? A friend of mine who's a machine learning whiz kid, he jumped out of an aeroplane with a bunch of rescue guys once in order to try and truly understand how they would make decisions, the commanders would make decisions on the ground and what sort of information they really needed. And I think we need to accelerate how we do that. Maybe not all jumping out of planes as machine learning experts, but getting to the point where you actually can understand how these people make use of this information, so we start to plug into real world decision-making systems. And I think there's still a journey on that. It's not very easy frequently because, people are making decisions based on a lot of gut reaction and a lot of other systems that they already trust. So bringing something new to them that might not have the same level of explainability might still be a challenge for them. So I think it's exciting, though. That's what we're on the cusp of now, I think.
Two things I want to see you jumping out of an airplane now, Simon, to do some of this. Looking forward to that. And that really does speak to the trusted and then useful, right? So that customer research for the people who are actually going to use this. I mean, like some of you, I get multiple texts per day on my iPhone about what the sun is doing. But so what? What are we going to do? And what a great way for us to understand. And Martin, it looks like you were nodding enthusiastically. Do you have something to add?
Absolutely. At the end of the day, all it really is a storytelling problem, right? How do you tell the story of what's going to be happening next with the data? And I mean, with Vigil and its follow-up missions at L5, that'll be an absolutely unprecedented view, pretty much, just with the potential for so many new correlations, or maybe even just all the correlations reinforced, to be found there, with the potential for new physics right there, which is just absolutely exhilarating. I mean, quite frankly, the work that the team's been putting in over the past couple of weeks, that's exactly what would be necessary to properly make use of that. So absolutely.
Yeah. Other thoughts? Please jump in, panel. Raul.
Yeah, I think, I mean, in the line of what Simon was saying before, in terms of how do we operationalize this, how do we make this available to the people who are going to really need it. I think we are in a very interesting moment right now. It is a moment where, on one side, we have lots of data available even for Earth observation or solar research and so on. And on the other side, we have all these fantastic AI methods promising a lot of potential for this data. And what we are doing here, we are working in the glue that is in the middle of all this. And this glue has several components. It's a part of engineering. It's very hard to get data fed into these machine learning pipelines, let alone talking about how we allow end users to feed themselves the data. It's a challenge for us as engineers already. There are challenges in terms of how well we define the problems we want to tackle, so we can actually tackle them with the tools that we have. Sometimes it seems that with AI we can solve everything, and it's not exactly that. We have to pinpoint very well the questions we are able to ask to AI. And then there is a third challenge in terms of how do we validate well what we do. In terms of Earth observation, we have the time dimension, we have the spatial dimension. There are uncertainty measurements that we want to be able to make available to the end users. So it is in this glue in the middle that I think the challenges and the interesting work right now are, and this is what I think this is what we are doing.
Excellent. Thanks, Raul. Freddie, Kelsey, Danielle, Gabrielle, any additional comments that you can add to this discussion?
Perhaps I can highlight the contrast here. We have a deluge of sensor data coming in daily, terabytes and terabytes of data. But unfortunately, maybe we have a few kilobytes of data that generate in terms of labels every month. So what we actually know what's going on the Earth requires human eye in the end of the day, right? And there is no replacement for that. No matter how excellent our AI is, how fast our computers are, the real bottleneck here is the ground truth data labeled by experts who really know what they're looking at. Until we get that, in the meantime, yes, there's other things, useful things we can do, like train these foundation models by using our deluge of satellite data, from which we can learn very useful visual primitives for our computers to store in their data banks. And when the time comes, when we have the labels, we can put them to good use. So we don't need that many labels to learn from, whatever that use case may be.
Thanks for reminding us of that, Freddie. Others, Gabriel, you're nodding enthusiastically.
Yes. If I can go for it. Sorry, Gabriel, go for it. Okay, thanks. Well, I tend to agree with Freddie on this aspect. It's true that we have many raw, in the sense, unlabeled data around, but when you consider, for instance, the application of AI onboard satellites, that in-Earth observation is something that nowadays has been explored a lot to provide not only actionable information, but also actionable information very quickly by using, for instance, intersatellite link or SMS from space, call it however you want. Well, when you see, for instance, the data that you need to process on board that are not calibrated, they are not registered at all, you will not find many raw data, but raw in the sense very close to what the sensor produce around. So this is actually a good challenge for speeding up the delivery of actionable information when you want to process on board.
Nice. Danielle. Oh, you're muted, Danielle.
What I was going to add on top, sorry, on what Fred and Gabriel was saying is that we have not only few data, but something that is very natural to the disaster response, let's say, challenge on itself is that we have very few data likely of what we want to find, right? And that adds another layer of difficulty on top of what we're already doing.
Thank you. And Kelsey, can you wrap us up here with maybe a couple things? What, hate to put you on the spot, but I'm going to, shame on me, but what can you imagine will our future with things like Vigil and other disaster aid technologies at the intersection of AI help us do? And what would you hope we do pay close attention to as we move into that future?
Yeah, I'm really excited about kind of echoing the sentiments that Simon made about the operational context of these works. I know that in another life, I used to be a solar flare researcher. They're so hard to model. There are multiple types of classes of flares happening very close in time to each other. So they're really, really hard to model. So I totally sympathize with the difficulty of these problems as well. So I'm really excited to see how these types of works are going to actually be integrated into like satellite operations and on-orbit mitigation strategies in the future, particularly for the solar flare project. So I think all these projects are really, really exciting, and it's going to be really interesting to see how we take these solutions and actually implement them into action. So I'm excited to see that, especially for the future of these very large satellite constellations that we have now.
Wonderful. Thank you for sharing that. I don't know about all of you, but I am filled with hope actually when I see these presentations for the things that we're talking about here today. And when you think about disaster resiliency for humans worldwide, it is really something to see how far we've come and to think about how far we're going to go to help more people be able to deal with floods and all of the other things that fires, etc., that matter to us. So thank you all for joining us on this panel. We are going to move on to, as I've promised, a bit of a fun thing at this point. And to do that, I'm going to bring up a couple of colleagues from the FDL team. Cormac, Catherine, I think you're both going to join us here as we move into the FDL Collaboration Awards, the annual FDL Collaboration Awards. So Catherine, take it away.
Thank you so much, Jonathan. So at its heart, FDL is about community. We come together every year as a community of researchers to collaborate with each other in solving these grand challenges. And the teams support each other and make these lifelong bonds while learning to think from new perspectives. So we want to celebrate the spirit with these yearly awards, as you say, are tokens of recognition for excellence in the most important aspects of the FDL community. Everyone, faculty and researchers at some point during the sprint has demonstrated all of the qualities that we look for in the awards. So this was a really hard decision. And just before we start, I'd like to give a special mention to Belina Raffi, our collaboration coach, for helping us once again with her magical sessions, and especially the 6 C's, which really paved the way to the right mindset that we have over the FDL sprint period: community, curiosity, compassion, courage, co-creation, and comedy. But without further delay, our first award is the most dramatic pivot. So pivoting is an action taken when new opportunities arise unexpectedly. And sometimes this means starting completely from scratch after much commitment is put into one idea. The Most Dramatic Pivot Award represents these changes in direction, at times unwanted, but certainly necessary.
And the winner of this award is the Solar Eruptions team for perseverance and pivoting several times to a very strong outcome. I think the Solar Eruptions team took on one of the hardest challenges and have arrived at the end of 8 weeks with a spectacular result. So congratulations, team, very well deserved.
Thanks, Cormac. And moving on to our second award for today, the Steely-Eyed Operator. So in every FDL project, there's a moment where everything can go wrong. This is the implicit contract of high-risk, high-reward research. And if you don't go through this, then your work just isn't new enough. Remaining clear-eyed and clear-headed in this moment is a rare quality, and without it, FDL wouldn't deliver. The steely-eyed operator acknowledges the efforts of a team member who has regularly been the calm voice in a storm.
And the award goes to Raul and Freddie for leading with both hands on deck and helping to do all of the difficult engineering work and developing code in absolutely record time. Raul and Freddie have been with us at FDL for many years, and they are a linchpin of our organization. Thank you, Raul. Thank you, Freddie. Brilliant.
Amazing. The third award today is the Unexpected Discovery Award. So just like dirty dishes helped the discovery of penicillin, and we know that melting chocolate bars triggered the creation of the microwave, the Unexpected Discovery Award represents this ability to stumble upon a breakthrough. As Plato once said, science is nothing but perception.
And the Unexpected Discovery Award goes to the SAR-FM team for developing sampling strategies that are game-changing and for using foundation models in the real world. We believe that the results coming out of here are going to be absolutely brilliant in terms of moving the needle on how we actually apply Earth observation data in the real world. So extremely well done, SAR-FM team.
Next up, we have the Heroic Comeback Award. So heroic comeback is an acknowledgement that when discovering something genuinely new, you have to first fail. But that's just one half of the story. Simply failing isn't enough. Getting back up, learning, evolving, and trying again is how legends are made.
So the Heroic Comeback Award goes to Hannah. Hannah pursued her work with relentless tenacity and helped guide the team in a mix of theory and experimentation. It was really Hannah's insight and guidance that helped make key breakthroughs. And Hannah, thank you so much.
Next up, we have the Collaborative Spirit Award. The Collaborative Spirit Award is the representation of FDL's beating heart, and that's interdisciplinary research. It supports the idea that to achieve great things, 2 or sometimes 20 minds are better than one, and the exchange of knowledge is key.
The Collaborative Spirit Award goes to the Biomass SAR team for exemplifying the FDL spirit, where each team member contributed to the results, and the result was greater than the sum of the individual parts. I've been very privileged to work with the team over the last 8 weeks, and I've really seen them like mesh together like a clockwork. Amazing, amazing.
All very well deserved. And our final award today is the Gaia Award. So, as Sagan observed, our planet is but a pale blue dot, a tiny speck suspended in a sunbeam. Yet within this speck lies the incredible capacity for life, a miraculous blend of elements and conditions that have allowed us to thrive. But this fragile equilibrium is easily disturbed, and it is up to us to protect it. The Gaia Award for Collaboration Excellence honors the team whose work best encapsulated these ideals. This team has embodied the concept that our strength is multiplied in unity. In a universe and an era that can be indifferent, they have chosen to pool their awesome talents and to weave a tapestry of data and algorithms with the potential to change things for the positive.
And I think, as you've already seen, it goes to the 3D Clouds team. Sorry for giving the game away early, but 3D Clouds team, extremely well deserved. Your work has the potential to have huge impacts on how we understand the future of our pale blue dot, as Carl Sagan said. So really looking forward to seeing what the project and where the project goes in the future, and well done, all of you.
Well done, and thank you, Catherine. Thank you, Cormac. All well-deserved awards from our researchers. Well, that's it for today. We do have just a brief wrap-up we'd like to do, and to do that, I'd like to bring James Parr back up on stage. James, my friend, I know one of the things that we certainly hoped for when we started this journey out 10 years ago, and specifically today, wrapped up on that. We want people to understand that artificial intelligence is not just a tool, but a beacon that signals a more positive future. We understand that the health of our planet's intricate systems, the atmosphere, oceans, forests, and countless other ecosystems depend on our ability to model things better, make smarter decisions, and formulate ways of collaborating more deeply. And we're certainly dedicated to applying the immense potential of AI to better understanding and care for the Earth, ensuring that we can continue to inhabit this remarkable world with reverence and responsibility. And I'd love for you to talk a little bit about something that you talk so well about, and that is wonder and gravity.
Well, actually, you know what? I might just before we, sort of change gears. I have to say, I'm just so kind of blown away and excited by what we've just seen. I mean, of course, we're privileged because we see, you know, the meal being made, but it's just so awesome to see this work. And I just wanted to take a moment to congratulate the teams for really digging deep, and also the faculty too. You guys have just, you know, hit an absolute home run. We're so proud of what you've achieved, and it's just, it's just extraordinary stuff. And
it is state of the art. There's no doubt about it.
Yeah, I mean, if you really dive into what they've achieved, it's really pushing the edge, and we're sort of hoping this work will be taken to Europe's and all the other big AI conferences, and that you can do us proud there as well. So I just wanted to take a moment to thank them, but also, you know, really the magic of FDL is this community that we've you know really you know come to help and support these problems. And you've met a few of the community already, the advisors who support all the teams, and they were on the panels as well, but also our private sector partners. So our you know, we couldn't do this without the support of them, in particular the compute providers. And so I just wanted to take a quick moment to shout out to the team at Lux Provide and the Luxembourg State Space Agency who supported the SAR work. Again, this is a really long-standing relationship. We've been working with Luxembourg for about 8 years, and just really so thrilled that we can start focusing on problems that are you know relevant to Earth action in particular. And you know, I guess this start we've made with this foundation model work is just really exciting. But also Guy, again, all of our flooding work has been dependent on Guy's expertise in the flooding, so we're very grateful for him. And then Google Cloud, like the massive amount of compute resource, and the fact that it's all linked together by this global backbone of fiber optics, which Google have put in place. This allows us to have these teams which are from all around the world working with these enormous data sets, and then this enormous compute resource to do what you've just observed. So we're just always so grateful for Google for being in our corner, and of course we couldn't do it without them. And similarly, NVIDIA, the GPUs inside Google Cloud, and we have other GPUs which are provided by our colleagues and friends at Scan Computers. And this, again, these are dedicated, massive A100 GPUs, which really allow the teams to scale their work. And so thanks so much to NVIDIA and Scan. And then lastly, just quickly, of course, you met them at the beginning, Guy, who I mentioned before, but also Alex Lavin at Pasteur and ISI, the Institute for Simulation Intelligence, really leading in the application for physics-informed machine learning for modeling. And Alex and his team have been crucial for our understanding of continuous learning and this big modeling that you've seen over the last couple of hours. So really, that's, I just wanted to take a moment to thank all that, and you'll see there really is a lot of people behind the scenes. A kind of you know, it takes a village to do the work that you've seen. Of course, our teams are the ones doing the massive work at the front end, but there's also this sort of pyramid of infrastructure behind them. And then, you know, really this, as I mentioned at the beginning, you know, this faith that ESA has put in us to take on these really hard open problems, these problems that no one's really been able to solve before, and give us this sort of, you know, room to do something which is really a high risk, high return bit of research. And we're just so happy and thrilled that we can continue this partnership with the ESA Lab. You'll see here there's some photos of what it's like. It's a really brilliant partnership. We're really so grateful, and again, thanks to them. So really, just to finish off, I just wanted to reflect a little bit on kind of I guess why we do this, and the sort of, I guess, this idea whenever I see this photo, and this of course is the Earthrise photo as the astronauts saw it as they came around from behind the Earth, and this is the first time really that human beings had seen the Earth, you know, at such a distance, and in 1968 over the Christmas. And this was, you know, this idea that we had the space program, but in the process we discovered our planet and the fragility of it. And I think, you know, we sort of realized that actually kind of we're now in this sort of moment where it's our responsibility to manage this small dot. You know, we can fly around it in 91 minutes. It's a it is a you know, very, very small oasis, and if we have the capabilities and if we have the brains, actually it is our responsibility to use them to solve these problems. So just really wanted to again thank everybody. In a way, you're all recipients of the Gaia Award, because all of this, everybody who's been involved with FDL this year has been sort of helping to, I guess, make our planet a bit safer and a bit, hopefully, a future a little bit brighter. There are a lot of people to thank, and you'll see them scrolling down on the page right now. But with that, I think we'd just like to say thanks, everybody, and we'll see you next year.
We will, and all of that for all of humankind. Right, for all of humankind.
Yeah.
So thanks, James. Good stuff. And thank all of you for joining us today. We hope you've enjoyed this, whether you watched it live or you're watching the recording of this later. And for more information, there are a variety of links presented throughout that you can take a look at. Thank you, and we will see you all next time. Take care. Be well.